3 going. Read the piazza. There's lots of discussion, lots of hints on how to do things. If you don't look at the piazza postings and hints, it's really difficult. If you look at it, it should be reasonably straightforward. Okay, so read that, please. It's not meant to be really difficult. It's meant to have you thinking about things, not fighting Python, it's an AI log, etc. Okay, any questions about anything? All right. So what we've been doing is we started off talking about probability theory. That's defined in measures of possible worlds. The possible worlds are the same possible worlds that we had when we did constraint satisfaction. There we just ruled out possible worlds and said that some were incompatible with the constraints. Now what we're doing is have this measure over possible worlds. And all we mean by a measure is this function from sets of possible worlds into a non-negative number. So we just need, given some set of worlds, just a value onto the non-real negative number. If you study probability theory, if you studied in mathematics, you'll end up with all of these funny algebras and Borel sets and all of those things just there because we don't necessarily do all of the sets of possible worlds. But they're all just functions from possible worlds into non-negative numbers. The measure of the set of all worlds is probability 1 just by convention, just we're defining it to be 1. There's nothing fancy about 1. You can actually do all of probability theory without without normalizing everything, but we'll normalize things. And the only real property we use is the measure of disjoint sets. The measure of the union of disjoint sets is the sum of the measure of the sets. And that's the only property, the only real axiom, the only real property of probability theory, and that's given everything else we're going to derive from this fact and the definition. The probability of a proposition of the measure of the worlds in which the proposition is true. We're going to talk about probabilities of propositions. And then conditioning on evidence as we make the worlds incompatible with the evidence have measure 0 and multiply the others to give a constant. So evidence just says these are impossible, let's make them all 0 now, and now let's just get this other posterior distribution. Are there any questions about that? Okay. So what we're going to do now is we're going to do some examples. All the arithmetic here is easy. You can use a bit of paper, but it should be really easy. Everything sort of drops out. And the reason we're going to do this might seem a really funny thing to do, is that these are all the operations that we're going to get the computer to do later. So all of the things we're going to do now are exactly the operations that when we also implement it, we're going to implement essentially the operations that we're doing now. So if you're doing it by hand, then you're going to say, oh, is that all it is? Okay, so it's going to be this. All right, so what I want to know is the only rule we have is when we have, so the measure of all the possible worlds, there's sort of 8 possible worlds here, and the measure of possible worlds, if you have disjoint sets, you can sum the probabilities, you can sum the measures. So I want to know what the measure of all the worlds where flu and sneeze is true. All right, how are we going? Does anyone need more time? Should be just simple arithmetic. You learned in grade 3 in school. Okay, let's stop. 3, 2, 1. Oh no. It moves, see? All right. I have to go back to question 1. Right, the answer is B. So it's 0.16. We're just going to add them. All right. What's flu and not sneeze? All right, how are people going? I think it was about 75. Let's stop now. 3, 2, 1. If you don't get it, don't worry. Right, the answer is 0.04, so it's A. Some people... What do people say? D, 0.4? No, there's a 0 in front of it. They're all little. Oh, deal with that. Let's go. All right, next one. What's the probability of flu? It's not on the clicker. What's the answer? I ran out of letters of the alphabet. You don't have an F on your clicker. Right, so it's 0.2. Right. We don't need to add up all the worlds. We don't need to add up all the worlds where flu is true because we've already added them up on the right. We have those two disjoint sets on the right, so we can add them. So 0.2. Right, so the answer to this one is 0.2. Oh, were there any questions about that? What about this one? What's the probability of sneeze given flu? Oh, this has... What's the probability of sneeze given flu? Oh, you don't need a calculator. If you can't divide by 2, you're in trouble. Oh, it is not hard. In a minute, we're going to get a computer that's going to do all this for us, but that's okay. All right, let's 3, 2, 1, we'll stop. Oh, that's exciting. Oh, the probability of sneeze given flu is, we did this, the probability of sneeze given flu is what? The probability of sneeze and flu. So out of all the worlds where flu is true, I want to know the proportion that sneeze is true. So this is, out of all the worlds where flu is true, this is the proportion that sneezes. So out of all the worlds where flu is true, I want the proportion that have proportion, I can't read, proportion with sneeze true. Can you read that? No, sort of. All right. So what's that? Flu and sneeze is 0.16. And you'll divide by flu, which we've already done, which is 0.2. And so we can divide by 2, and you get is 0.08 over 0.1, and then that's... Is that right? Oh, what was the answer there? E. Oh, wasn't that hard, the division, was it? All right, does that make sense what we're doing? Out of all, we're just selecting those worlds, and we're just renormalizing things. All right, one more to... We're going to collect up all these statistics so we can do the other ones. What's the probability of not flu and sneeze? I'll just do this one quickly. All right. I'll do it quickly. I just went great. OK. Hang on. You can do that. OK, 3, 2, 1, stop. The answer's C, it's 0.24. Oh, I can't get this to work. Oh, well. Click. All right. All right, so it's going to add up those two values, so the answer here is C. All right, so now we have enough statistics, we have enough information now to do this one. What's the probability of flu given sneeze? So oh, sorry. We didn't do sneeze, did we? Flu given sneeze. How are we going? Let's do 3, 2, 1. Oh. Okay, we'll stop. The answer is 0.4D. All right. So what we've done. So notice what we've done here is now we've got this. So one of the ways of viewing this is when we observe sneeze. So if you look at the difference between C and F, sorry, one is about flu and one is about when we observe sneeze, the probability of flu goes up. Right? So when we observe sneeze, so if we observe sneeze, the probability of flu goes from 0.2 to 0.4. Okay, and similarly, the probability of sneeze was, what is the probability of sneeze? What's the probability of sneeze? You guys just did it. What is it? Someone tell me. 0.4? And when we observed sneeze, when we observed flu, sneeze went from 0.4 to 0.8. So now it's about, now what's the probability of, if I observe both the flu and snore, you just got to add two numbers and divide by 1. I'll wait till we just get a sample of this. Okay, let's stop here and not grade it. Oh, I just won't grade it. We'll just stop it. Okay, the answer is 0.8. And what's interesting about this is that if you look, what's the difference between D and G? If you look at D and G, we note the probability of sneeze given flu. Sneeze given flu is equal to the probability of sneeze given flu and snore. So snoring tells us nothing about, in this data set, in this statistics here, snoring tells us nothing about sneeze if we know flu. Right, so snoring tells us nothing about sneezing. if we know flu. So if we're given flu, knowing snoring doesn't change the probability of sneezing. And the last one, I want everyone to guess. Don't calculate it, just guess. You have to guess. And then snoring tells us nothing about sneezing. If we know flu, there's a hint. Just guess how people are going for guessing. Oh, guessing you're faster, good. Let's stop, let's go. And the answer is 0.4. And that's right. Because we know that essentially that not only does flu tell us nothing about snoring when we know sneezing, it also tells us nothing about sneezing when we know snoring. So the probability of flu given sneeze and snore is equal to the probability of flu given sneeze. Snoring is sort of irrelevant in this interaction between flu and sneeze. Okay, does that make sense? So here we're talking about how to essentially, this conditional probabilities tell us how we're going to update our beliefs based on evidence. Right, so if we knew someone had the flu, whether they snored or not, tells us nothing about sneezing. It's going to turn out that if you actually calculate the probability of sneeze given snore, snore is relevant to sneezing. You might be surprised. But all right, any questions about this? All right, good. So it should make the rest of it much more straightforward now. Okay. So far we've just added. So far we've just been able to add probabilities, and that's all we need to do, and then divide to get conditional probabilities. We can also work out the probability of conjunction. So if the probability of H given E is the probability of H and E divided by the probability of E, which we derived last time, what's the probability of H and E? What is it? Right, so it's the probability of E. Just multiply both sides by the probability of E. It's the probability of H given E times the probability of E. This is sort of an instance of what's called the chain rule. We can use it for the probability of conjunctions we can do from these probability of conditional probabilities. So now let's do it in the more general case. We have a whole lot of formula F1 to Fn. So what we can do is we can just divide one of them off, and it's just a conjunction of one of them with the rest of them. So we can pull Fn out, and then so it's Fn given the probability of all the others times the probability of all the others. So that's just exactly the same rule that we did on the previous slide. We've just got a conjunction of F1 to Fn minus 1 is and Fn. So we can just put brackets around the left one, and we get the same one as before. Now I can do it again to this conjunction on the right. So in this conjunction, this second conjunction, we can do the same thing again, and we get f of n times f of n. We replace that by f of n minus 1 times f of n minus 2. And if we keep repeating it, we end up with the probability of f of n times f of n, all the ones, the previous ones, times f of n minus 1 times all the previous ones, times f of 3 given f of 2, 1 and f of 2 times f of 2 given f of 1 times f of 1. So all of them given the previous ones in the ordering. Okay, so once we have this, we just have each variable given the previous ones in the ordering, and we'll write it as this product, the product of the probability of f of I given all the previous ones in this ordering. Okay, does that make sense? We're just repeating that formula over and over again. We're just stripping one off and just replacing it with the previous ones. This is called the chain rule of probability. Okay, any questions about that? We're going to use this lots. And everyone knows this notation. This is familiar to people. This is the product of all of them. Okay. Now there's a famous theorem called Bayes' theorem. And we're going to know that conjunction is commutative. So H and E is the same as E and H. So we can swap the E and H around. So what's the probability of H and E we saw before was the probability of H given E times the probability of E. So what's the probability of E and H? What's the probability of E and H equal to? What's another way it's equal to? What is it? Yeah, but let's just swap E and roll of E and H in here. We know it's equal to this. What else is it equal to? Well, it's equal to the probability of H and E. What else is it equal to? It's equal to that thing up there. So what else is it equal to? There's another way around. We can, yeah. Times the probability of H, right? That's just swapping those, so just replacing E on that just swapping the role of E and H in there, we get this formula, right? So now what we're going to do is we now have these formulae. Probability of H given E times the probability of E is equal to the probability of E given H times the probability of H. And now what we're going to do is we're going to divide both sides by the probability of E. So now the probability of H given E is what? So what's the probability of H given E? The probability of H given E is what? If we divide both sides by the probability of E, what do we get? Come on, you can divide that. Grade 10, no, 9. Yeah.
Probability of E given H multiplied by the probability of H and divide the whole thing by probability.
Right, does that make sense? That's called Bayes' theorem. So there's all of things called Bayesian statistics, and it's named after this person who discovered this rule here, who used this rule for computing all sorts of interesting probabilities. All right, so that's Bayes' theorem. Has anyone heard of Bayes' theorem before? All right, good. Few people. Who hasn't? Few people. Okay. So why is it interesting? Well, it's interesting for us because often we have causal knowledge. We have knowledge about how the world works, the probability of a symptom given to disease, the probability that the light is off given the status of the switches and the search positions, given that if there's a fire, how reliable is the alarm? Given that there's a tree in front of a car, what does an image look like? So we have sort of graphics information. And what we want to do is to do what's called evidential reasoning. What we'd like to do is, given a symptom, we'd like to find out what the disease is. So we'd like to reverse these conditions. So given we observe the light is off and we observe the switch positions, we'd like to know the probability that some switch is broken. Right? Given that there's an alarm, we'd like to know the probability there's a fire. And given an image that looks like that, we'd like to know what the description of it is, the probability there's a tree in front of a car. Okay, so we're going to talk about this causal knowledge. We're going to talk about this evidential reasoning, and that's typically what we have to do. We typically observe the world, but the sort of models we have are the other way around. That's why Bayes' theorem is interesting. Okay, any questions about this so far? Okay. Let's do another little exercise here. This is actually from a psychology experiment from Daniel Kahneman. So cab was involved in a hit-and-run accident at night. 2 cab companies, the green and the blue, operate in the city. You're given the following data. 85% in the cabs, the city are green, and 15% are blue. A witness identifies the cab as blue. The court tested the reliability of the witness in the circumstance that existed on the night of the accident and concluded the witness correctly identifies each one of the 2 colors 80% of the time and failed 20% of the time. What's the probability the cab involved in the accident was blue? So what's it about? This is actually a psychology experiment. What's it approximately? And then we'll work it out exactly. What's it approximately? Yell out some guesses. Yeah. Hmm? 0.15. The cab involved was blue. Hmm? Sorry? I'm just guessing this.
Sorry, that's not my guess.
Oh, that's a good guess. We'll leave it. What's your guess then? Okay, you haven't got a guess. Okay, we'll leave this one. What's another guess? If you're a policeman, what would you suggest? Was it blue? They said it was blue.
Just
15 times 80. I don't know how to do that. So that's 0.12. Around 0.6, someone said. Good. That's what we want, guesses. Someone else? Yeah.
The second guess plus the probability of...
Oh, we know how to compute it. We just want to get.
Yeah. Okay.
What's it?
Oh, I just wanted to give you
Yeah, the ball pass.
So that first guess plus 0.2 times 85%.
This one.
No, second guess.
This one.
Plus. Okay, can I explain why I'm giving you the answer before you, because you can see there. Okay, so you need that. You need the probability of that the guy said it was blue when it was blue, and you need the probability that he said it was blue. You need to compare that to the probability that he said it was blue on the screen. So because you need to zero out the answers. You know what I mean?
Yeah, I know what you mean, but these people don't.
The probability of success and the probability of failure need to add up to 100%. So you can't just say 0.12 because there isn't an 88% chance of failure.
Right, so the probability, let's do it properly. The probability that it is blue, given that they said it's blue, is equal to what? No. That's the other one. That's the what's the probability that? What's the probability? Let's work. What's the probability that they said it's blue? Sorry, given that it is blue. Which of these are we given? These are different, right? What's this story tell us? Hmm? We want this one. We want this one, right? What's this one? Coordinates, yeah. Right, this is 80%. That's what the reliability means. If it is blue, they're going to say it's blue with probably 0.8. So how are we going to do this? Which rule would we use?
Yeah, base this equals the right part times is P of is blue divided by P set blue.
Right, is blue times the probability of is blue divided by the probability that, what is that? Said blue. Oops, I can't.
Maybe witness is right than
Hmm?
Maybe witness is right is better than set blue because it's not implying that it's just saying that the witness said it's blue or the screen it was correct.
Well, no, they said it was blue. We don't know if they're correct. In fact, that's what we're doing. We're trying to work out whether they are correct. So this is 0.8 times the probability that they is blue. What's that? According to the story? Times 0.15. Divided by the probability they said the blue. Well, they either said the blue. If they said blue, it's either said blue and... So this, notice this one here, this top, is equal to said blue and is blue. So this top, this thing here, is the probability that they said blue and is blue. So this one said blue is equal to the probability they said blue given that it is blue is 0.8 times 0.15 plus they said blue and it isn't blue. So that's the probability they said blue. So 0. Times it is blue, yes. That's not right. So this is said blue and is blue. What's this one? This is said blue and is green. So this should be, so this is said blue and is blue. Said blue and is blue. Oh, we have a green. Good. This is said blue and is green. Said blue and is green. And if you do this, if you have a calculator, I think it's 0.41 approximately. So even though they're 81% reliable, even though the person's 81% reliable and they say it's blue, it's most likely it's not blue because you have to take the prior probability of things into account. So when we do any of these things, if we do any of these things, we have to take the prior probability of things into account. We need the prior probability that you have some disease that's going to affect all of these things. And then we're just updating it based on observations about the world. Okay. Right, so this is just Bayes' rule. We just need it as a... Okay, any questions about that? So now we're going to do this notion of conditional independence. And so random variable x is independent of random variable y given random variable z if the probability of x given y and z is equal to the probability of x given z. So what this means, in the notation we've said before, is for every x in the range of x and j in the range of y, and for every yk in the range of y, and for every zm in the range of z, that the probability of x given y and z is the same even if I change z, even if I change the y. So that's what's important here. I've got this y is yi here, and here the only difference in this is y is yk. So changing our minds in here, changing the y's doesn't affect the probability of x if we knew z was true. So the probability here of x, and it's also just equal to the probability of x given z. So knowing y is irrelevant. So if we did this, so in this example here, what independence is true? What's independent of what? What independence is true in this example we just did earlier? So what independence was true? Yeah. Flu is independent of snore. Oh, hang on. Is that right? Yeah. Sneeze is independent of snore. What else might be true? In fact, both of these are wrong, by the way. What? Yes, flu is independent of snore given sneeze. Sneeze is independent of snore given. Is that right? Sneeze is independent of snore given flu, right? So if we know something of it, so it turns out in this example here, with the way I constructed it, was that the previous independent assumptions were not true, but these conditional independencies are true. So we're talking about given some other things. It's this conditional independence that we're going to talk about is, for us, is going to be the most interesting thing. Okay, any questions about that? All right, so let's look at this. Our domain we've been looking at before. I'll just find this quickly. Oh, there. And now we're going to have all sorts of independence assumptions we're going to make about the world. Silly ones like the identity of the Queen of Canada is independent or dependent of whether there's light is lit given whether there's outside power. Right, so there's all of these things we're modeling, and essentially we're going to say that all the other things are irrelevant. They're all independent given this variables. Maybe there's going to be some rioting in the streets if we and then become a republic and all sorts of things, but never mind that. Okay. So whether there's someone's in a room is independent whether light is lit. So whether someone's in a room influences whether light. It's very highly correlated with whether the lights are lit, right? But is there something that renders them independent? Hmm? Well, maybe. Right, depends on where they are, but what else does it depend on? Yeah. Right, given the switch position, right? If you knew the switch position, whether the person was in the room or not is sort of irrelevant to you. Okay, so whether you know, if you know the switch, the only way they're going to affect the light is by affecting the switch. So there's this independence assumption we're going to make about given the position of the switch. So now we're going to say whether the light is lit is independent of the position of S2. So we're talking about light L1 is independent of S2 given what? In this diagram up here on the left. Yeah. So there's something, if I knew it, would render them independent. Well, no, but then switch 1's still going to, switch 2 is going to affect the light. No, Steve, if you're given switch 3, then switch 2 is dependent on light. Because if I switch the light's going to go on and off. But if I knew what, how does switch, it's one of the ways to think about how does switch 2 affect light being L1 being on? Sorry? It does. If you change switch 2, light 1's going to go on or off. But if I knew something, what's independent? Okay, there's something more obvious than that. Yeah. Yeah, if you knew whether there was power in Y 0, then it's independent, right? So if you knew there's power in Y W0, and in fact, what does L1 depend on? It's independent of everything else given what? So L1, so whether light L1 is lit, it's independent of everything given what? So what does it only depend on? Yeah, it only depends on Y0 and sort of whether it's working okay. Whether there's power in Y0 and whether it's working okay. It doesn't depend on anything else. That's all it depends on. So there's this very local, modeling the world in a very local way. L1 only depends on YW0 and whether the light's working. Okay, so what we're going to do is we're going to define something called a belief network or a Bayesian network. And what we're going to do here is L2 is lit, depends only on the status of light L1 and whether there's power in W0. So we're going to have a variable here called L1 is lit, and it's only going to depend on whether there's power in W0 and whether the status of light 1. And I'm going to write them as in a graph as the parents. And what it's going to mean is that everything else is independent given these parents. So it's just an independence assumption. So it's a graphical form of writing these independence assumptions. And W0 here depends on what? What is W0? Where there's power in W0 depends on, if you look at this, what does it depend on? Right, it depends only on the position of switch 2 and whether there's power in W0 and whether there's power in W1. And whether it's broken or not. It just only depends on those things. So there's this. Okay, and so this is, we're going to write these graphical models, so-called graphical models of, and they're models of conditional independence. So here's what we're going to do. Is we're going to start off, we're going to totally order the variables that we're interested in. And then we got the chain rule, which says that we can divide up, what's the chain rule? Says we can divide this probability of the conjunction in the product of all of these variables given their predecessors. So all the variables given their predecessors, we're going to divide up into this form here. And the parents are those of xi are the predecessors of x that render them independent of the other predecessors. So if we knew them, everything else is irrelevant. So those ones before x that render it independent. So the parents are the subset of it that, given the parents, it's the same as being given all the predecessors. Okay, so that's how we're going to write this. The probability of xi, so we're defining the parents to be those variables that if we just given the parents, it tells us everything else we know. So we know that this is the chain rule again. So if we know this, then we know, so this is just the chain rule with this independence. The probability of the conjunction of x1 to xn is the probability of xi given its parents. And so this belief network is just a graph. The nodes are random variables, and there's an arc from the parents of each node into that node. And that's what we're going to mean by a belief network, just a representation of conditional independence. So here's an example belief network. Let's get this. Oh, there. Okay. So what we're going to do is we're going to look at, So what we're going to do is we're going to think about here what depends on what. And we might start off the ordering with tampering. Let's look at the relationship between fire and smoke. Right, so if we know something about tampering, and we know something about fire, maybe they're independent of each other. Right, but now let's look at smoke. What does smoke depend on? What does smoke depend on in a... What might you expect? No, totally wrong. Assuming these two are independent of each other. Tampering is just someone playing with a fire alarm. They're not affecting the fire. They're just playing with the fire alarm. They're independent of this. What does smoke usually depend on? Fire. So smoke depends on fire. So we're going to write smoke depends on fire. And now we're going to have an alarm. What does the alarm depend on? Let's suppose it's one of the alarms like that one up there, like those little sprinkler alarm things. What does that depend on? It depends on tampering. Well, there's two different sorts of smoke alarms, one of which depends on fire and one of which depends on smoke. Right? So there's different sorts of fire alarms. There's smoke detectors, but I'm going to assume it's one of these other ones that actually depends on the heat of the fire. And tampering here doesn't depend on smoke at all. Okay. And now we're going to have people leaving. They hear a noise. What does the leaving depend on? Oh, sorry, that's not tampering. What's that? Alarm. When do people leave the building? Right, it's sort of just based on, Right, so people leave the building based on, and so it says that the leaving doesn't depend on the tampering, it only depends on the alarm. It doesn't actually depend on the fire, it only depends on the alarm, but the alarm here depends on the fire. Yes, that's what this assumption says. That's what this says. Well, that's fine, but this is our model. But we're going to build different models, right? But each model means this. This means this. So this means exactly that the leaving doesn't depend on the fire, it only depends on the alarm. Okay, that's what this model says. It doesn't depend on smoke. Okay, then you could say this is not a very good model, but this is my model I'm going to use now. Okay? But we're going to write all sorts of different models, and they're going to make different independence assumptions. And if we say everything depends on everything else in some funny way, then we have a big mess. But if we build a model where things depend on only a few things, we'll get it much easier. And here someone in another And so now we have some of the other stories that there's a report. Only depends on the leaving. It doesn't. Someone tells us in another building, everyone's leaving the building. It only depends on the leaving. It doesn't depend on the fire or the tampering or the smoke. So here's a model, a simple model, that's sort of a simple Bayes net model that we can build. And we'll play with it next time and see what sort of inference we're going to do with this. Okay, so conditional independence, that's all this is a representation of. Okay, let's stop there.